तो कैमरा तो वहाँ पे ऊपर है ना, ये वाला कर देते हैं तो कैमरा। हाँ वो कैमरा ऊपर लगा है। उधर उधर
हाँ उधर से स्टेज दिख रहा है, ये वाला एक्टिवेट कर देंगे तो उनको ऑडियंस दिखेगा।
Oh, that is one. That leftmost screen is already the.
हाँ
Oh, now it's swiveled around. Earlier it was showing this.
right.
अनिरुद्ध भाई कैमरा को खाली थोड़ा साफ कर देना। अनिरुद्ध भाई
It is this very tough.
अरे पांच बार कैमरा ऑन करे तो पीपल लिंक वाला।
It is so
हाँ
light.
हाँ वो टीपी लिंक पीछे वाला कैमरा है, उसको थोड़ा क्लीन कर देना।
Warm layers. A summer picture.
सेंटर में कर दो, सेंटर में।
सेंटर में एक वक्त खाली क्लीन કરી દેજો, ક્લીન એના ખાલી કપડું ફેરવી દો ને ખાલી। હા બસ ચાલશે, બસ 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 અને વધારે ના ચલા હલાવો।
हाँ हाँ
સીધો કરી નાખો, આડો છે।
हाँ, कर दो 1 मिनट। बराबर ना?
આડો છે હજી થોડોક આડો, ઉપરથી ટિલ્ટ કરો ને થોડોક, ઉપરથી આમ સેજ વાળો। હા બસ 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 બસ, ઓકે ડન, ગુડ। હા ચાલશે, ઓકે ઠીક છે। ખાલી એક આંગળી ફેરવી દેજો કેમેરાને।
The equivalent of the speaker being photographed, the screen is being photographed.
Well, in that case, the screen should be the right screen, right? Let me do that.
True, true.
All right.
Yeah, nice. So we're all set to start. Welcome back, everybody, to the afternoon session, last day of FSTTCS and the last of our invited talks today. Today we have with us Suguman Bansal. Well, we have with us in an online way, so to say. And it's my pleasure to introduce her. Suguman is at the School of Computer Science in Georgia Tech University in the USA. She obtained her doctorate degree from Rice University, where she worked under the supervision of Moshe Vardi. She then did a postdoctoral fellowship at the University of Pennsylvania, where she was mentored by Rajiv Allur. Her main research focus is formal methods and logic, and their applications to various other settings, including artificial intelligence, machine learning, programming languages. So formal methods, logic, AI, ML, PL. And as her webpage says, her long-term research goal is to build trustworthy AI. We're all waiting for that. And her current research themes are formal methods as applied to formal methods for reinforcement learning, reactive synthesis from high-level specifications, and also, I think, symbolic quantitative reasoning. So these are the three themes that she's currently focusing on actively. And in keeping with the first of these themes, her talk today is about logic-guided reinforcement learning. So we're looking forward to hearing. Suguman, over to you.
Thank you, Meena. Thank you for the wonderful introduction. It's an honor to speak at FSTTCS. I'm very grateful to the organizers for giving me the opportunity, and more so for letting me do this remotely. I have a 3-month-old baby at home, and I've realized that that puts a lot of restrictions on travels. So thank you for letting me do this remotely. The talk I'll present today, which is on using logical specifications in reinforcement learning, is based on joint work with several collaborators, mentors, and students over the years. And the very, very broad theme of this work is to build trustworthy artificial intelligence through tight integration of formal methods and AI algorithms. Now, AI is ubiquitous. It is present in voice assistants on our devices. It's used in healthcare for medical diagnostics, autonomous vehicles, recommendation systems, IoT devices, social media. AI is ubiquitous indeed. In fact, AI is no longer the future. It is the present we live in. And AI systems today are extremely good and effective, so much so that when I asked ChatGPT to build me a slide on the ubiquity of AI, it gave me very, very detailed instructions on what I could do. It even gave me a very dramatic tagline to add to the end of the slide. But fun and games aside, there is a lot of skepticism to using AI in real-world systems, especially in safety-critical systems. Present-day AI systems have routinely violate safety and trust concerns. They are opaque, they hallucinate, they don't explain what they do, and the list goes on. But the lack of trust in AI systems offers an opportunity for formal methods research. After all, formal methods is in the business of building safe, reliable, and trustworthy systems. And formal methods has had immense success in building trustworthy hardware and software. And the arc has been incredible, starting from purely theoretical work all the way up to large-scale industrial adoption. So, of course, the question that many of us in the community have been working on is whether formal methods can be used in building trustworthy AI. Now, there are fundamental challenges behind fundamental challenges to using formal methods in AI, which differ remarkably from how formal methods was used in hardware and software systems. So suppose, for example, consider the problem of synthesis. Now, the synthesis problem says, given an environment and a specification, can we automatically build a system that satisfies the spec? Traditionally, in formal methods, we assume that the environment and the specification are known. We can model them precisely. Now, given this, we expect that the system that is synthesized gives deterministic guarantees of correctness. Now, this may not be possible for AI systems. For starters, the environment may be very large, it may have complex dynamics, and it may be hard to model. For example, suppose we were to synthesize a room navigation robot, then the environment in that case would be the physical room. And modeling a physical room precisely is very, very challenging. Similarly, the specification may be imprecise, it may be non-rigorous, there may be noise, sometimes parts of the specification may not be available, and so on. So in the synthesis of AI systems, we need to work under such assumptions on the environment and specification. And in fact, it's not surprising if we do not get deterministic guarantees of correctness anymore. So if we think about what the problem of synthesis of AI systems entails, not only do we require new synthesis approaches, we also require new notions of trust in order to validate the systems that are synthesized. So today's talk, we'll focus on one such synthesis approach. We will look at the synthesis approach of reinforcement learning. This is a data-driven machine learning approach to synthesize systems. And the question we will ask is, how can we build trust in reinforcement learning? So now that the stage is set, let's look at what the problem of reinforcement learning is. It has diverse applications across robot manipulation, autonomous systems, finance, software bug finding, and so on. But at a very high level, RL is a synthesis problem. It says, given a task, can we generate a policy that accomplishes it? The defining feature in reinforcement learning is that the environment in which the policy will operate in is assumed to be unknown. So the policy can be learned only by sampling the environment. In particular, the policy samples the environment, and based on that sample, the environment returns feedback, which the policy uses to update itself. And this process continues, the cycle continues until the policy can't be updated any further, or the policy can't be improved any further. So you should really think of reinforcement learning algorithms as this policy iteration loop that has repeated sample and repeated learning from feedback. Traditionally, in machine learning, the task of reinforcement learning is expressed in the form of a reward. Now, and that could be a bottleneck because expressing long horizon complex tasks as a reward can be quite challenging. For example, suppose we had a really simple task, and the task was to reach a given point P from the initial state. Then the corresponding reward function for this task is actually quite simple. It simply assigns a positive reward upon reaching the target state and gives a 0 reward otherwise. But suppose I make the specification a little bit more complex, and now I say, well, we want to reach P and then we want to reach Q. Now observe, we can't simply take the reward function of reach P and the reward function of reach Q and concatenate them one after the other. Because if we did that, we would not be able to prevent undesirable behaviors that reach Q without ever visiting P. Now, if you think about this for a little bit longer, you will be able to design an appropriate reward function even for this specification. But it's quite clear that as the task becomes more and more complex, writing this reward function can become cumbersome. An alternate to rewards are temporal logics. Temporal logics are used to describe properties over executions. They can describe logical constraints over executions, such as Boolean predicates propositions and Boolean operators. And they can also express temporal constraints over executions. Over the past many years, several temporal logics have been proposed, both within the formal methods community and the AI community. And the common benefit of temporal logics over rewards is that they have rigorous semantics and their syntax is easy and their syntax is very close to natural language. For example, for the specification to reach Q, the temporal logic is simply eventually P. And if you want to reach P and then reach Q, simply concatenate eventually P with eventually Q. Therefore, an emerging area of research is to design reinforcement learning algorithms where the task is given in the form of a temporal logic specification as opposed to using a reward function. And the question we will ask today is, can temporal logic specifications be used to build trust in reinforcement learning algorithms? At the onset, we can at least say that when it comes to task specifications, temporal specifications have an advantage as they are rigorous as opposed to rewards that are non-rigorous. Through this talk, we'll try to evaluate whether temporal logics really can be used to build trust in reinforcement learning algorithms by analyzing the theoretical guarantees they offer, as well as the algorithmic performance of these algorithms. So this is going to be the outline of the talk. We're going to try to fill in this table. So let's start by formally defining the problem of reinforcement learning. The environment in reinforcement learning is given by a Markov decision process, an MDP. So it consists of states S and actions A. Note in the most generality, both S and A could be infinite in numbers. So we are not restricting ourselves to the case where the number of states or actions are finite. There is a transition probability function, which assigns a probability on transitioning from one state to another, given an action. And there is an initial state distribution, which tells us what the initial states in the MDP are. So here is an example. This is a 9 rooms environment. It is an infinite state MDP. States here refer to the points in the Cartesian plane. So any point xy in this plane is a state. Actions correspond to tuples such as theta d, where theta is an angle and d is a displacement. The transition probability function assigns a high probability on going to the correctly calibrated state from a state given an action. And with very low probability, perhaps the action fails. So you maybe go to a fail state. And the initial states here simply correspond to the region, the blue region shown on the slide. So any state here is an initial state. Policies in an MDP is simply a map from executions in the MDP to a distribution on what action to take next. So a policy simply informs a reinforcement learning agent on what action to take next based on the history of execution. Now, the problem of reinforcement learning from rewards is defined as follows. Given an MDP and a reward function, which assigns a reward to every transition and a discount factor, assuming that the transition probabilities of the MDP are unknown, can we generate a policy that optimizes the discounted sum reward? Now, the critical factor here is that we assume the transition probabilities are unknown. And this is what we formally mean by saying that the environment in reinforcement learning is unknown. Now, note that suppose the transition probabilities were known, then this is the very well-known, very well-studied problem of MDP optimization. So if we were given an MDP, a reward function, a discount factor, and we wanted to find the optimal policy with respect to rewards, given that the transition probabilities were known, this is the problem of MDP optimization. It is extremely well studied. Seminal results from 60 years ago tell us that there exists an optimal policy, and this optimal policy is both memoryless and deterministic. And because the policy is memoryless and deterministic, one can use what are called Bellman equations in order to find this optimal policy. Now, I won't go into the details of what the Bellman equations are and how they are set up, but all we need to know is that in order to solve the Bellman equations, we need to know what P is. That is, we need to know what the transition probabilities are. So this approach to solve Bellman equations cannot be used in the case of reinforcement learning from rewards because P is unknown. So in the absence of transition probabilities, what we say is that we assume that we have a simulator of the MDP, which gives us 2 functions. One function that says that we can always go back to an initial state, and another function that lets us sample actions from the current state in the MDP. But give and take, what these 2 functions allow is the ability to sample as many executions as one wants in an MDP. So the problem of reinforcement learning is effectively saying that given the ability to sample executions in an MDP, can we find an optimal policy? So at a very, very high level, the 10,000 feet view of how reinforcement learning algorithms work is that we first simulate, we first sample many, many executions in the MDP. We use these executions to estimate what the true underlying probabilities are. Once we have a good estimate of the transition probabilities, we can now use the Bellman equations in order to obtain the optimal policy. So that's the very, very high level view of how reinforcement learning algorithms work. And in terms of the kinds of theoretical guarantees one can get, reinforcement learning from rewards offers asymptotic guarantees of correctness. What this means is that if one could sample till infinity, then we are guaranteed to converge to the optimal policy. The other kind of guarantee that reinforcement learning from rewards offers are PAC guarantees. PAC stands for probably approximately correct. which means that there are algorithms which can converge to a near optimal policy with high probability after a finite number of samples. So to put this in perspective of the goal of this talk, in terms of theoretical guarantees, rewards offer guarantees of offer asymptotic as well as pack guarantees. So the next question is, what about temporal specifications? So starting from scratch, let us formally define the problem of reinforcement learning from temporal specifications. The problem of reinforcement learning from temporal specification says, given an MDP and a temporal logic specification as opposed to rewards, once again, assuming that the transition probabilities are unknown, can we generate a policy that optimizes the probability of satisfying the specification? Note, unlike learning from rewards, now we want to maximize the probability of satisfaction. We are not maximizing a reward anymore. For example, in this 9 rooms environment, suppose our specification was to eventually reach the region S1, then any policy that can generate trajectories that will eventually reach S1 is an optimal policy. Now, once again, if we had the ability, if we knew what the transition probabilities were, then I claim that one can easily learn the optimal policies using a sampling-based approach. And let me demonstrate this through a really simple example. Here I have a 3-state MDP consisting of 3 states, an initial state, a safe state, and an unsafe state. If one takes action B from the initial state, there is a small probability of reaching the unsafe state, and otherwise it reaches the safe state. Now, suppose the specification is to always avoid the unsafe state. Then it's quite clear that in this MDP, there is only one optimal policy. And that is the policy which takes action A from the state initial. Because any other optimal policy, any other policy will have a non-probability chance of reaching the unsafe state. So there is only one optimal policy here. Now, if we knew what the transition properties are, then the question is, can we learn the optimal policy using only a finite number of samples? And I claim we can do that. And in fact, there's a really simple procedure to do it. And here is one algorithmic approach. Suppose P min is the least non-zero transition probability in this MDP. Then what we could do is we could sample every action from every state around 1 by P min times. And if we do that, then there is a very, very high chance that we have a good estimate of what the true underlying probabilities are. Right? In particular, we would know what transitions have probability 0 and what transitions have probability non-zero. And once we have a good estimate of transition probabilities, then this is simply the problem. Then we can easily set up the appropriate Bellman equations and obtain the optimal policy. So if the transition probabilities are known, we can easily design a sampling-based approach that can obtain the optimal policy using only a finite number of samples. Now let's see what happens if we don't know the transition probabilities. That is, what happens in the reinforcement learning setup where transition probabilities are unknown. So it's the same MDP. There is only one optimal policy. The optimal policy is to take action A from initial. And we ask the same question. Can we learn the optimal policy using a finite number of samples? But now we don't know the transition probabilities. So here is a scheme, right? Here's a very general scheme. Suppose from every state, you sample every action K number of times. And K is some parameter in the inputs. Note K cannot depend on the transition probabilities because those are unknown. Now suppose we sample action B from initial K number of times. Let's look at what happens here. If K is not large enough, in particular, if K is smaller than 1 by gamma, then it is possible that none of our samples will discover the edge that goes from the initial state to the unsafe state. And if we never discover the edge that goes from the initial state to the unsafe state, we might as well learn that the optimal policy is to take action B from the initial state. Because all our samples have seen is that upon taking action B, we only visit the safe state. The issue here is that because we don't know what gamma is, we actually cannot estimate how many samples are required in order to ensure that we will always see the transition from initial to unsafe. Now, one can take this intuition further, and we can prove that in the case of reinforcement learning from temporal logics, we cannot design an algorithm that gives a pack guarantee. In particular, there is no algorithm that can ensure that after a finite number of samples, one can learn a near optimal policy with high confidence. So this might seem like a bummer, but fortunately, one can counter the pack impossibility by making few assumptions. And some of these assumptions include assumptions on the MDP. So for example, we saw that if we knew P min, then we can learn the optimal policy with pack guarantees. There are other assumptions that one can make on the MDP, such as knowing the topology of the MDP or knowing the mixing time, under which one can get pack guarantees by learning from specifications. However, the practitioner's view is that assumptions on MDP is not correct in the context of reinforcement learning, because the whole idea is that we don't know what the environment is. So we can even show that by making no assumptions on the MDP, but by making assumptions on the length of executions that will be sampled, we can still learn with pack guarantees. And this includes some of my own work with the collaborators. So to summarize how far we've gotten so far, in terms of theoretical guarantees, learning from temporal specifications does not have pack guarantees in the most general form. However, pack guarantees are available under assumptions. And the question of whether asymptotic guarantees exist is still an open problem. So the question was, can we build trust using temporal specifications from RL? In terms of theoretical guarantees, it is a mixed bag so far. Now let's go to algorithmic performance. What is known about learning from rewards is that learning from rewards is extremely effective in learning short horizon tasks. However, they do poorly on long horizon tasks. I won't get into why this happens. Let's just take that at face value for now. The question is, how do temporal specifications fare? So the algorithmic template of reinforcement learning algorithms from temporal specifications is as follows. We start with the problem of reinforcement learning from temporal specifications and reduce it to a problem of reinforcement learning from rewards. And then we solve the problem of reinforcement learning from rewards, and whatever policy is obtained from that is taken to be the policy of the original problem. The reason we rely on this reduction is that algorithms that learn from rewards are extremely scalable and extremely scalable and efficient. And therefore, this algorithmic template lets us leverage all the existing work that the machine learning community has done to learn from rewards. Note that none of this approach, of course, does not have guarantees of correctness, because we've already shown that pack is not possible. But as a practical approach, this approach lets you leverage the existing work in learning from rewards. However, what we show is that what we have been able to demonstrate is that this algorithmic approach is actually not very scalable. And here is an example. Suppose we take this really simple, we take this 9 rooms environment. The initial state is S0, and we have the regions S1, S3, S2. Suppose and O is an obstacle that we want to avoid. Suppose the task is to visit S1 or S2 while avoiding the obstacle O. Then this graph here plots the performance of several existing reinforcement learning algorithms that learn from specifications. And here on the x-axis shows that the number of samples that have been taken, and the y-axis shows the probability with which the policy learned so far satisfies the specification. And we can see that many of the existing algorithms are able to learn this task quite well. So an algorithm is good if it has a more steeper curve. The higher the curve, the better. The closer to probability 1, the better the curve. And we can see that many existing algorithms are able to solve this short horizon task. But suppose we make the task one step more complex, and we say that after visiting S1 or S2, we also want to visit the state S3. Now the performance of all existing algorithms diminishes immediately. The reason this happens is that in the first case, reinforcement learning algorithms can learn to visit the region S2. And learning visiting S2 is easier because it's an obstacle-free path. So in the first case, between the choice of visiting S1 and S2, it was much easier to learn to visit S2, and therefore that is what most reinforcement learning algorithms do. In the second case, however, in order to visit S3, the only way to visit S3 is through S1. And in fact, it is futile to learn to visit S2. So in this case, what a reinforcement learning algorithm is missing is the high-level perspective that although visiting S1 may be challenging in the short horizon, in the long horizon, that is the more effective task to learn. And that is exactly what we are able to overcome by using logical specifications in reinforcement learning. In fact, we have an algorithm called DIRL, which incorporates high-level reasoning on the logical specification with low-level reasoning of reinforcement learning algorithms in order to effectively learn long horizon tasks. So this temporal specification we use here is called spectral. It consists of reachability and safety constraints. Eventually is a reachability constraint, always is a safety constraint. We can concatenate such constraints and we can take their disjunctions. What we have shown is that spectral specifications can be used to generate a DAG-like abstraction of the underlying environment, such that every edge in the DAG corresponds to a subtask, and every path from the initial state to the final state in the DAG satisfies the specification. So in this running example of visiting S1 or S2, then visiting S3 while avoiding the obstacle, the corresponding DAG is this 4-state graph with states S0, S1, S2, S3. S0 is the initial state, S3 is the final state. Every edge corresponds to a subtask. So the edge between Si to Sj corresponds to the subtask of visiting Sj from Si while avoiding the obstacle. And every path from S0 to S3 satisfies the given specification. Now the benefit of this DAG-like abstraction is that it gives rise to a very natural compositional algorithm to learn from specifications, where the decomposition phase simply makes use of the first property, that every edge is a subtask, and the composition phase makes use of the second property, that every path from initial to final satisfies the spec. So the composition algorithm is rather simple once we have these two things, that in the first phase, one will learn a policy for every edge. Because every edge is a short horizon task, one can use an existing reinforcement learning and off-the-shelf reinforcement learning algorithm to learn that task. And once you have a policy for every edge, we now want to find a policy for the overarching task. And for this, we simply need to compute the best policy from the initial state to the final state. Best is, of course, with respect to the path which has the maximum probability of satisfaction. And although a priori probability of satisfaction for every edge is unknown, but once we have learned a policy, we can estimate the success probability along every edge. And once you have the success probability for every edge, one can use any simple path-finding algorithm to find the best path from initial to final. So in this case, in the decomposition phase, we will learn the policies pi1 through pi4, one policy for every edge. We will learn that the policy from S2 to S3, policy pi4, has extremely low probability of satisfaction because there is no path from S2 to S3. And therefore, the best path from S0 to S3 is the one which follows pi1, then pi2. So the best policy here is to go from S0 to S1 while avoiding the obstacle, and then going from S1 to S2. Now, this is a fairly simple algorithmic approach, except that I left out one little key detail, and that detail appears in the decomposition phase, where we want to learn a policy for every edge. The issue here is that a priori, we can only sample policies from the initial state. So we only have the ability to sample a policy from initial state S0. We cannot sample an execution that begins in S1 or that begins in S2. And if we can't sample an execution that begins in an intermediate state, we can't learn a policy that starts in an intermediate state. So in addition to learning policies along edges, we also need to learn a state distribution for all of the intermediate states in the DAG. And without going into too much details here, all I will say is that it is possible to learn state distributions for all intermediate states in a manner that is extremely efficient. In fact, we can show that one can learn a policy in a DAG by a single sweep of the DAG. So, and by making as many reinforcement learning calls as there are edges in the DAG, which means that for every DAG, we need to learn only a policy only once. And by choosing the order of learning policies along the edges in the right way, we can do it in a single sweep. So in theory, this algorithm is extremely efficient because we can also show that the DAG is efficient in the size of the specification. In practice, these algorithms are extremely efficient as well. And we show that these algorithms do extremely well in scaling to long horizon tasks. So here I have a 16 rooms environment. It's very similar to the 9 rooms environment, except that it is larger. The red blocks here correspond to obstacles. And I'll use the shorthand box X to Y to denote the specification, which means from X, visit either one of the corners C1 or C2, and then visit the region Y, and all the while avoid any obstacle that arises along the path. So suppose we look at the specification box A to B, then this plot shows the performance of several reinforcement learning algorithms that learn from specification. Our algorithm DIRL is shown in blue, and we can see that among all of the algorithms, our algorithm has the best performance. But one can make the specification longer, and we can say that first the specification is box A to B and then box B to C. And we can see that while DIRL maintains its performance, other algorithms begin to deplete in performance. And we can keep making the specification longer. We can say box A to B, then box B to C, then box C to D, or we can make it even longer. And we see that as the specification becomes longer and longer, competing algorithms degrade in performance. However, DIRL is efficiently able to scale even to long horizon tasks. Similarly, DIRL is also able to scale in the dimensionality of the environment. So a higher dimensional environment is more complex. And here we've been able to show that even on simulations of Baxter robotic arms that is available through OpenAI Gym, which is an open source reinforcement learning library. Ours is the only algorithm that is able to learn long horizon tasks. No other existing approach is able to learn in high dimensional environments. So when it comes to the performance of learning from temporal specifications, when it comes to the performance of learning, when it comes to performance of reinforcement learning algorithms for long horizon tasks, one can leverage the structure of temporal logic in order to scale to long horizon tasks, as well as scale in the dimensionality of the environment. So we started by talking about trust, and in terms of theoretical guarantees, there's a mixed bag. And in terms of algorithmic performance, we know that these algorithms perform well empirically, but there is no explanation to it. And that indeed gives rise to the first future direction I want to talk about, which is, can we bridge the gap between the theory and the practice of learning from specifications? In particular, so far we know that there are pack guarantees are available only under assumptions, and asymptotic guarantees are open, but the performance is extremely strong empirically. The question is, can one build new tools and theory to explain the algorithmic performance? And this is somewhat inspired by an article published in an opinion article published in CSEM, which said that the role of theoretical computer science is to explain and predict real-life computing. And a venue like FSTTCS is ideal for this sort of work, which brings together researchers from theory A and theory B. And the ability to bridge the gap between theory and practice will require tools and techniques from both communities. So the future direction is what kinds of tools and theory can one build in order to explain the algorithmic performance of reinforcement learning algorithms from temporal specifications. The other direction we want to talk about is of certification. So far in reinforcement learning, we were only learning the policy, the desired policy from the task. But what if we also learn a certificate for the task? You can think of a certificate as an artifact which can be verified by a third party that can ensure the correctness of the given specification. So there is a very, very rich literature of certification from temporal logic specifications when the environment is known. For example, when the temporal logic specification is a reachability goal, then the certificate is simply a ranking function. But all of the existing work in certification is when the environment is known. So you can think of it as current work on certification applies to non-AI systems where a precise model of the environment is given. So there is an opportunity to build the theory and practice of certification in the reinforcement learning setup where we assume that the environment is not known. So this would give rise to purely sampling-based algorithms and what kinds of guarantees they can offer if one has to simultaneously learn a certificate. And then one could think of opportunities of trying to use the certificate to inform the learning of the policy as well. But one can go beyond, and this is also another way of trying to build more trust in reinforcement learning algorithms. But one could also think of problems beyond just scalability and performance, and also focus on other pertinent issues that synthesis algorithms generally have. For example, most existing synthesis algorithms lack generalization. What that means is that even if the underlying specification or the environment is changed even in the slightest, then one has to learn or synthesize from scratch. For example, if I had a policy that can navigate from R0 to the goal state and from R1 to the goal state, no synthesis approach would be able to take the policies for these and extrapolate them to learning a policy that could navigate from R2 to the goal state, R3 to the goal state, and so on, despite each one of these tasks being a small deviation from the previous task for which we know what the policies are. In some of the work that I've been pursuing with my graduate student, we have been able to leverage the logical structure of temporal specifications in order to learn generalizable policies, but all of this work is empirical. So we've been able to show that if we have policies that start from R0 or start from R1, then we can extrapolate a policy that starts from R2 or from R3. However, none of this work has any theoretical grounding. To the best of my knowledge, there is no existing theoretical foundations to formally define what the problem of generalization is, and certainly no work that can tell us why logical structures are effective, why logical specifications are effective in enabling generalization in the context of learning or synthesis. So to summarize today's talk, we started with the question of, can one use logical specifications in order to build trust in reinforcement learning algorithms? On the onset, we said, in terms of ease of task specification, temporal logics are more rigorous and therefore build more trust. In terms of theoretical guarantees, PAC is not available under the general reinforcement learning assumptions, but certainly can be achieved under light assumptions on the environment or on the specification. And although algorithmic performance is extremely strong empirically, we don't have any theoretical understanding of why that happens. So to build trust in reinforcement learning algorithm, we have only been able to scratch the surface with what could be possible or what specific temporal logic is able to bring to the table. There is still a lot of opportunity for future work, and work that perhaps requires integration of theory A and theory B in order to build trust through means which go beyond theoretical guarantees of correctness. And these could be through ways of trying to explain empirical performance. These could be through certification, or these could be through understanding other facets of synthesis algorithms that go beyond performance and guarantees. And at a very, very high level, what this tells us that in order to build trust in AI systems, one needs to go beyond, one not only needs to design novel algorithms, but you also need to go beyond the traditional notions of trust in order to satisfy the needs of existing AI approaches. If you're interested in learning more about these techniques, you can follow our tutorial, which appeared at AAAI on specification-guided reinforcement learning. And with that, I conclude my talk. We can open the floor to questions.
Thank you, Suguman. Questions? Okay, the mic will go around, and please wait till it reaches you and speak only into the mic. Otherwise, the speaker is not going to be able to hear you. Yeah, sure.
Hi, Suguman, Srihasan here.
Okay.
Thank you for the very nice talk. So I'm just wondering about the column 2,2 with temporal specifications, theoretical guarantees. So there are, so I'm wondering if you add some sort of probabilistic temporal specifications. I want to reach only with a certain, I'm okay to reach unsafe state as long as the probability is not too high. You incorporate this sort of reasoning into the temporal specification, do you get some theoretical guarantees?
Right. So the formulation of reinforcement learning that I gave I presented today is all about learning the optimal policy. But your question is, what if I say that, well, you can learn with probability greater than P? Am I understanding your question right?
No. So I'm saying the temporal specification is not LTL, but like a probabilistic PTL. What is it? Probabilistic temporal logic. So you have eventually and so on, right? Because as I understand, when you wanted to reach this unsafe state, you don't have enough number of samples to say, I cannot, I mean, no policy should reach that. It's like reward minus infinity, right? In some sense. So I'm wondering if instead in the temporal specification, if you could say that, I mean, I'm okay to eventually, I mean, not of unsafe, or I don't want to reach it, but if I'm okay to reach it with utmost probability, let's say P. Just essentially change the LTL to PTL and do the same again. Do you get guarantees? That's the question.
So my intuition is that it would still not help because we are still not able to mitigate what the fundamental issue is. The fundamental issue is that you don't know how many samples to take, right? So right now we say, well, if I don't know how, no matter how many samples I take, there could be an MDP where the number of samples I've chosen is insufficient to be able to learn the policy that I require. And the same issue still persists, even if you have a PTL kind of specification. Because suppose you say, well, I'm okay to visit the unsafe state with probability 0.2. You still don't know how the dynamics affect, how the dynamics of the MDP affects the 0.2 probability, right?
Right. Okay.
Because there is still that gamma factor. You still don't know.
It works with rewards, but not with temporal specification. Anyway, yeah.
Yeah. So the reason it works with rewards is because we were looking at discounted sum rewards. And in discounted sum rewards, and this is the fundamental difference between rewards and spec. In rewards, you can say, if the goal appeared 10,000 steps away, then maybe the 10,000 steps away is not so significant. And that not significant gets absorbed into the with high probability near optimality criteria. But that doesn't happen with temporal specifications because, for example, in reachability, whether you reach within 1 step or you reach within 1,000 steps, the contribution to the probability of satisfaction is the same.
Yes, so that's the thing. So I'm okay with reaching it after 1,000 steps, let's say something like that. So it has to incorporate into the logic. I mean, you can incorporate whatever happens in the rewards into the logic itself.
Yes.
But maybe we can discuss offline. Yeah. Thanks.
Yeah. But perhaps I can add one thing to this discussion, and I didn't go into much detail here during the talk. And that's what I meant by assumptions on the length of the execution. Suppose we say, well, we want to bound the length of the executions. Okay. Suppose every execution can be only of length 10. Then pack is possible.
I see. Okay.
Right?
Okay. Thanks.
Yeah.
Okay. A question there.
Hi, thanks. Really nice talk. I had a question regarding this gap in performance between the short term and the sort of the short horizon and the long horizon situation. So, uh, just to understand this setting a bit, like when you're saying that you're measuring the performance of existing algorithms on this A to B, then B to C, then C to D kind of tasks.
Mhm.
How do you, within this reward setting, even mention something like go from A to B first and then from B to C? Because you might just get a reward if you go from B to C even without visiting A first, or even, yeah.
Yeah. Yeah. So that's exactly where and that's the issue I started with, right? That if you only have rewards, you want to A to B, then B to C, it's very easy to just go to C and never visit B, right? So that's where that decomposition plays in, that you have a temporal logic specification and you purposefully decompose it. If you're trying to solve it without decomposition, you will run into this issue. But if you purposely decompose it appropriately, and we have an algorithm to do it, then you condition your algorithm on saying that you have to first go from A to B, then you go from B to C. And the way we did it is by saying, well, you look at the DAG structure. The DAG structure automatically gives you subtasks. Each one of those subtasks needs to be, any subtask that appears on a path from initial to final has to be satisfied with high probability, right? So we said that the optimal policy that we will generate, will be along the best path from initial to final. And if you're getting the best path, you are implicitly saying that for every subtask, each subtask should have been satisfied with high probability. So that is how we enforce that each subtask is satisfied along the way. Does that answer your question?
Yeah, just a small follow-up. I mean, just trying to understand if when we specify a task in terms of this LTL kind of thing, is there like, are we able to say more just because we have an LTL specification versus a list of rewards for certain states or transitions? Because with LTL, we can encode a lot more into the spec as opposed to just having a set of rewards, right?
Yeah.
Are we seeing something of that nature in that example is also would be my follow-up question.
Perhaps what we are saying is that temporal specifications can naturally be decomposed. Reward functions, to the best of my knowledge, don't have a nice decomposition approach. So if I give you a very sophisticated looking reward function, it's not clear how you can decompose it into smaller subtasks.
Right. Okay. Yeah.
Another question here.
Hi. So I had a question regarding so you might be aware about the shield synthesis topic, right? So there the automata theoretic approach is used to give guarantees. So could you compare this with that approach?
Yeah, absolutely. So the setup of something like shield synthesis is slightly different from what we are doing. What we say is that so perhaps the best way to describe is that suppose you had a safety property. Then what shield synthesis will say is that at every step, so reinforcement learning is about exploring and exploiting, right? So you explore the underlying MDP by taking samples of executions, and then based on what you explore, you learn the best policy. In something like shield synthesis, it restricts the exploration. So if you have a safety property, it will restrict the exploration to only the safe states. So you will never visit an unsafe state in shield synthesis. But that could still happen when you're saying, so in that sense, and then the guarantee you get there is that assuming you could only explore within the safe states, then we can find an optimal policy. So that's the kind of guarantee you get in shield synthesis. But here we say that we don't put any restrictions on the exploration part, right? So they're slightly different setup in that sense.
Yeah. So just a small follow-up on that. So we are trying to make specifications, right? Like with temporal logic. So there are much more expressive logic as already pointed out. So like in probabilistic specification expressions, like something like for monitoring or stuff like that. So do you expect maybe like using automata where we don't have a difficulty of specifying in a way, or we have a transition diagram to describe how these things are for infinite state systems, which is analogous. So something like that would help or will overcome the trouble of specifying in logic.
Is the question about specifying in logic, or is it about trying to get guarantees from these specifications? Could you clarify that?
Yeah, so basically trying to get guarantees at the end, but maybe we are saying that pack under assumptions happen to be one of the features of this. So I was wondering if we could maybe perhaps take like automata theoretic approach or different approach. Is it going to help us or something like that?
Yeah. So that's a very good question. So my intuition is not. My intuition is that no, you won't get a lot of benefit by looking at another form of specification. And partly that is because if you look at the example I presented, the example is a simple safety spec. It's nothing complicated, right? It's perhaps if you look at the hierarchy of specifications, safety and reachability, like safety and single reachability, are among the easiest specifications that exist. Now, it doesn't matter whether you represent it using LTL, you represent it using an automata, you represent it using some other high-level specification approach. The fact that you can't solve safety with pack guarantees is already a very strong fundamental limitation. And in fact, one of the papers I cited during this in the talk is a paper by Michael Littman's group from Brown. And they actually strengthen our pack impossibility result by giving a necessary and sufficient condition for pack possibility. And they say that in reinforcement learning from qualitative specifications, so this could be any qualitative specification, pack is possible only when you restrict the length of the executions. Under any other assumption, you cannot get pack guarantees. And this is already that's a stronger result than even the proof I demonstrated during the talk. So my intuition is that no, simply changing the specification language will not make a difference.
Okay, thank you.
Hi. You said that ranking functions are certificates when the environment is known. Can you comment a bit more on that? And what does it mean to certify when the environment is totally unknown?
Yes, so this is based on literature that mostly comes out from, I mean, these are formal methods people, but they do cyber physical systems. So if you have a reachability constraint, a reachability specification that says you want to reach from position A to position B, then if you have a policy, the certificate tells you whether the policy will satisfy the reachability goal. And in this case, the certificate is a ranking function, which simply intuitively tells us what is the distance of a current state from the goal state. So as one makes progress towards the goal state, the expectation is that the ranking function will decrease in value. So that is the intuition behind ranking functions being certificates for reachability constraints. Now, the thing is that if one wants to learn a certificate, provably correct certificate, then knowing what the underlying MDP becomes important. Again, as I said, that you can think of the ranking function as simply a function that tells you what the distance is. So if you don't know what the underlying probabilities are, you can't tell what the distance are, what the distance from the target state is. So which is why I said that learning certificates without knowing the underlying MDP is still an open problem. And that is perhaps where one can try to just come up with theoretical results of whether it's possible to learn a ranking function, under what are assumptions required, or can one learn ranking functions with guarantees without any assumptions and so on. Does that answer your question?
Thanks.
Thanks.
So I have one short question about the explain performance part. So your long horizon task algorithm, it repeatedly used a rewards based algorithm for the short horizon task. And
Yes.
we know that in the short horizon setting, we have asymptotic guarantees, which are not going to help because you're making these calls repeatedly. We have
Yeah.
path correctness, but then even then, what I don't understand is why don't the errors add up and go out of control? So is this again where you're using the fact that your eventual execution length is bounded, or?
So our algorithm right now has no theoretical guarantees of correctness. We only can talk about what we see empirically. So
It seems to be doing well. So somehow the errors are magically canceling each other out.
exactly, right. And which is precisely what we don't understand. And this is where I think, this is why I think FSTTCS is the right venue to even discuss this problem. As a formal methods researcher, I don't know what the measures are to explain performance, but I'm hoping that somebody from theory A can explain that to me. So I think question is better answered by experts in theory A, who do have better measures for how online algorithms work. And one can perhaps think of reinforcement learning as an online algorithm. So yeah, short answer, I have no clue. I don't know what it means to explain performance of algorithms. And I would actually redirect this question to to better experts.
Okay, thanks. Let me check once more. Any more further questions? Oh, there are more questions.
Thank you for the great talk. So, in the machine learning community, we have this idea of RLHF, reinforcement learning from human feedback. So, do you think this specification we can give you, say, guarantees or even notions of trust, for example? So, how would that fit in?
Sorry, your voice was muffled. Could you repeat the question, please?
Okay. Is it better?
Yeah.
Yeah, so I was asking about how does this fit in the idea of RLHF when you are doing reinforcement learning with human feedback? So, do you think it can do better guarantees with that? Because you can, so the functions. So, can we update our specifications iteratively or something like that? Can it happen?
Yeah, that's an interesting point. Okay, it's another. So if I understand the question correctly, it is would human feedback somehow help learning from temporal specifications? And I think yes, there are ways in which that could happen. For example, let's look at the diagonal approach I showed, which takes a long horizon tasks and breaks it into shorter horizon tasks, right? Now suppose I had a specification, and maybe it will help if I go back to, let me quickly go back to, whoops. Did I stop sharing my screen?
Yes.
Oh, okay, my bad. So let me quickly come back to this example I had. And perhaps I can demonstrate the point. Where did the example go? Here we are. Slideshow from current slide. And I want to share my screen again. Yeah, so here we have, let's look at the second specification, right? The specification says visit S1, S2, then visit S3. Now, suppose the specification here was simply visit S3. Then then the DAG in the case of visit S3 would simply be a single edge DAG, right? That has S1 on one end, S3 on the other, and nothing else. So if you had, what I'm trying to hint at is that in this case, that short horizon task is actually a long horizon task, but the specification did not have the granularity to present what the shorter horizon tasks were. However, if we had human feedback, then perhaps we could have somehow informed the algorithm that, hey, by the way, maybe it will help if you introduce S1 or S2 as a sub-goal. And then if you have S1 or S2, one could basically achieve the performance that we do on a specification like this. So this is one way of using human feedback in order to decompose the specification to better granularity for reinforcement learning algorithms to learn each subtask better. And I'm sure there could be many other ways in which one could incorporate human feedback to improve performance.
Okay. Are there any further questions? No. Okay, then please join me in thanking Suguman once again for this very nice talk and interaction.
Thank you.
Yeah. And our local organizer, Neil tells us, so all the invited speakers who are here were presented as a memento, a puzzle, which should keep you busy for a long time to come. And Hara assures us that a puzzle will be snail mailed to Suguman and you will get it eventually. Yeah.
All right. All right. Do I have to solve the puzzle, or is it fine if I don't solve it?
You have to send proof.
I have to send a certificate of at least attempt to solve the puzzle.
Yeah. Thank you so much. Yeah.
Thank you very much. Thank you for the invitation, and thank you for the lovely interaction.
Okay. So we have a short break now before we begin.